All right, guys, let's start. Okay, so now we are doing the lesson number 3 of your chapter 1. So lesson number 3 of chapter 1 is about your introduction to boundary and initial conditions. Okay, so that's the whole aim. Let's dig deeper, try to understand what do we exactly mean by boundary and initial condition, why we need to be very careful here. Okay, so a partial differential equation alone is like saying the option price must follow this equation, right? But that is not enough, right? We also need to say what happens at maturity, what happens when stock price becomes zero, what happens when stock price becomes very large, what is the current state of the market, right? This is what your boundary and initial terminal conditions do, right? So the concept is partial differential equation. Simple meaning is the role of evolution. Okay. In financial meaning, how option value changes with time, price, volatility, rate, etc. Then the concept is boundary condition. Simple meaning is what happens at the edges, stock price near zero or very large. When the concept is initial condition, simple meaning is your known starting value, financial meaning is current portfolio or market value. Terminal condition is simple meaning is known ending payoff. Financial meaning is option payoff and maturity. Unique solution is simple meaning is one correct answer. Financial meaning is one economically meaningful price, right? So that is what we have. Okay. Again, if you look at this particular slide, right, we are kind of doing the introduction to boundary and initial condition. The lesson is part of the PDE, partial differential equation chapter in quant finance. The important point is before solving partial differential equations numerically or analytically, we must know the conditions that pin down the correct financial solution. In quant finance, partial differential equations are used in your option pricing, actual PDE, interest rate products, bond pricing under Vasicek, or your CIR model, or risk management, your scenario-based valuation in weeks, portfolio optimization, dynamic value function, XVA, counterparty risk, valuation, underfunding, collateral grade adjustment. So this slide prepares us for the practical question, right? How do we make a mathematical PD represent a real financial contract? Okay. All right, let's try to dig deeper and understand more. Now, here, right, in the next part, right, we'll try to understand why boundary and initial conditions kind of matter. So this is the core idea of the lecture. The slide says that the PDE by itself usually has infinitely many possible solutions. To get the correct one, we impose extra condition. Think of it like as without condition, many possible mathematical answer, with condition, one financial meaningful answer. PDE incomplete, with condition, PDE becomes solvable. When without conditions, there is no link to contract. With condition, link to payoff or market behavior. Without condition, not tradable. With condition, can produce price, leaks, risk number, etc. Right? The key example given in the slide is this. V of S comma T equals maximum of S minus K and 0, meaning P is equal to your option value, S is your underlying asset price, T is the maturity date, K is the strike price, max S minus K is equal to the call option payoff. For a European call on maturity, if S is less than K, you have call payoff 0, S is equal to K is 0, S greater than K, S minus K. So the terminal condition tells the PDE that at maturity, the option value equals its contractual value. This is very important because the actual pricing is essential. Start from the known payoff of maturity and work backward to today's price, right? To solve a partial differential equation uniquely, it is not sufficient to specify the equation alone. Additional constraint in the form of boundary condition and initial terminal conditions are required. Mathematically, PDEs admit infinitely many solutions unless such conditions are imposed. These conditions lack the financial meaningful solution. Role in quantitative finance. Boundary condition describe the behavior of financial variable of extreme values of state variables. And so, initial or terminal condition import contractual payoffs, option value, maturity. Together, they translate real world financial constraint into mathematical form. And as I told you, example, European option payoff for expiry, portfolio value at the current time, interest rate level is specified boundaries. Okay. Very, very important. Terminal condition tells the PD, for the example, which is given that at maturity, the option value equal its contractual payoff. Very important because actual pricing is essentially the same thing. Start from the known payoff at maturity and work backward to find out today's price. Then in the slide number 3, right, we have again the same two equations which you studied in your lesson number 1, right, of chapter 1. So Dirichlet and Neumann, right? So those two things we have to understand, right? So the boundary condition has been given, specify the value of the function at the boundary. which is given v of x comma t equals g of t, meaning at the boundary the value of the function itself is fixed. In finance, this means we directly specify the option value at some edge of the domain. This is one of the vital equation which we saw in the lesson number 1 also, right? So remember that part, okay? Of this chapter only, lesson number 1, guys. If you want, you can go back and see that. So I said, right, in this equation, right, in your Dirichlet equation, right? So very, very important, right? The Dirichlet boundary, the Dirichlet condition, because we are fixing the actual value at maturity, right? In financial interpretation and maturity t value condition or example condition is ds t to the max s minus k comma 0 at s equals 0 for call b0 to 0 at s tends to infinity for put vst tends to 0, right? So financial interpretation is given most common in option pricing and used to specify terminal payoff. Then we have Neumann boundary condition, which is kind of fixed gradient, right? We have, right, the formula is given partial derivative of b with respect to x at x comma t equals h of t at the boundary. We do not fix the value, we fix the slope or sensitivity. In finance, this is usually about Greeks. For option pricing, we use similar kind of thing, which is called option delta also, right? So Dirichlet fixes your value. Financial meaning is option price or payoff. For Neumann, it is derivative, delta sensitivity, mixed. For Robin is value plus derivative, which used in your some numerical financial models, right? Again, what you need to understand, limiting delta behavior for large asset prices. For the deep in the money European call, you have to see that when the stock price is extremely high, the call behaves almost like the stock itself. So the delta approach is kind of one, right? So understand these examples. These have already been discussed in the previous chapter also, right? I'm not stressing too much here. Then we get into the initial conditions. Initial condition in financial PDE. Slide defines initial condition in the state of the system at infinite time. T is equal to T naught formula. Px comma T naught is equal to V naught x. V of x comma T equals your V naught of x, meaning at the starting time, the function is known in finance. This could be your initial condition example, current asset price, meaning S naught is known today. Current portfolio value, portfolio starts from known NAV, current interest rate, R0 is known today. Current volatility level, sigma 0 or V known is known today. Important distinction here is that, kind of. So as I was saying, right, see what is important to understand here is that if you look at your equation, right, V of x comma T naught equals V naught of x, right? In the starting time, the function is known in finance. This could be the initial condition can be current asset price, meaning S naught is known today. Your initial condition could be current portfolio value. Also, portfolio starts from known NAV. Current interest rate R naught is known today. Current volatility level sigma 0 or V naught is known today. Important distinction is you have type initial condition, which is today or starting time, terminal condition, maturity or ending time. In many finance problems, especially option pricing, we usually solve backward in time. So the price or the most important condition is often the terminal payoff rather than the initial condition, right? So that is very, very important. Okay. So yeah, so initial conditions specify the state of the system at the initial value, the initial time. They are essential for solving time-dependent PDEs where the solution evolves forward or backward in time. In quant finance, initial conditions represent observable market information at the current time. The asset price, current option value, the initial portfolio value, initial volatility of interest rate level. Mathematically, initial condition takes the form of this, where V naught x is a known function describing the system at time 0. Without initial condition, a time-dependent PDE admits infinitely many solutions and has no financial meaning, right? So that is what we try to understand. Then we have your slide number 5, which is about your boundary and initial conditions quantitative finance, right? So basically, boundary and initial conditions are essentially in financial PDEs because they translate contractual features of derivative into mathematical constraints. European option pricing, Black-Scholes model, the pricing PDE is all backward in time. The payoff and maturity provides terminal Dirichlet condition, which is given. It is, again, we have studied it already. Initial condition time is 0. The option price is observed as V S not equal to V not S. This represents the current market value of the option as a function of the underlying asset price. This condition ensures the PD solution matches both the option payoff structure and the market prices. So this particular slide explains the concept directly to European options pricing in the Black-Scholes. Right, the slide says pricing PDEs, pricing partial differential equation is solved backward in time. Payoff at maturity gives terminal Dirichlet condition. Current time value may be represented as Vs, 0, 0, V naught S. The key formula Vs, T equal to max S minus K, 0. V of S, T equals max of S minus K and 0. This is the European call payoff. And how to think about it? Basically, at maturity, there is no uncertainty about the option payoff. It is mechanically determined by S and K. Situation maturity, as we have discussed earlier, also stock is below a strike, option expires worthless. Stock above strike, option pays S minus K, stock equal to strike, payoff is 0. Please understand, right? And it is given that V S, 0 equal to V naught S, right? But in standard actual pricing, the thing we usually want to solve for is today's option price, right? V S naught. So practically normal option pricing. Thermal condition means known payoff and maturity. PDE solution gives current option price. Current market option price is used for calibration checking, not usually the input condition, right? So a better way to say it, in Black-Scholes, the terminal payoff is known as T. The PDE is solved backward to obtain Vs naught. Okay. Then we get into the next part, which is understanding your graphical view of your PDE domain. The diagram shows a rectangular-like region, horizontal axis asset S, vertical axis time T, bottom edge or initial time T equal to 0, top edge maturity T, left edge boundary S equal to 0, right edge boundary S tends to infinity. For option pricing, we solve the PDE over the full region. What each edge means is that top edge T is equal to T, right? That is the terminal condition Vs T to max S minus K, 0. Left edge S equal to 0, boundary condition V0 T, equal to 0. Right edge S tends to infinity, boundary condition Vs T is equal to S minus K exponential minus RT minus T. Bottom edge T equal to 0, current value. Final result we want, right? The diagram is the foundation of finite difference method. In finite difference pricing, create a grid over S and T, then fill in values using terminal payoff, boundary condition, PDE recursion backward in time. Right, so that is what we have, right? Okay, then we get into this part, interpretation of the diagram, which I told you, right? The slide introduced the Black-Scholes PDE. We have the full equation, which is partial derivative of your V with respect to time plus 1/2 sigma square S, 1/2 sigma square S square times the second partial derivative of V with respect to S square plus R S times the partial derivative of V with respect to S minus RV equals 0, right? So if you look at the first term, right, this is what, right? This is your change in value per unit of time, right? Theta term, right? It is time decay changing the absolute value, right? Then if you look at this term, right, what is this? This is gamma volatility term, which is convexity effect due to uncertainty. Then we have next term, which is delta drift term, change due to risk neutral growth of stock. And then we have last term, which is discounting term, which is basically present value effect. Why your boundaries matter here? Because the PD tells us how V behaves inside the domain, but it does not tell us what happens at the edges. So we need S is equal to 0, right? And S tends to infinity. S is equal to 0, stock cannot go below 0. S tends to infinity, we need limiting option behavior. T is equal to T is basically contract payoff becomes known, right? And T is equal to 0, today's price is calibrated, a total price obtained kind of thing, right? So this is exactly why boundary and terminal conditions are not optional. Without them, the PDE is partial differential equation is mathematically kind of incomplete. Okay, so please understand that. Then we get into the next part, which is kind of summary. So this is short chapter, boundary and initial conditions in quantitative finance. Boundary and initial conditions are fundamental components in solving partial differential equation, particularly in quant finance. These conditions define the financial problem being model, ensure the PDE admits a unique and economically meaningful solution, translate the real world contractual and market constraint mathematics. Financial interpretations include option payoffs at expiry, terminal boundary condition, current asset or portfolio values, initial condition, sensitivity of behavior at extreme price or maturity, boundary constraints. Without appropriate boundary and initial condition, PDE-based financial models cannot produce realistic, stable, or tradable prices. Understanding and correctly specifying these conditions is therefore essential for accurate pricing, risk management, and portfolio optimization model financial markets, right? So again, the slide is basically summarizing the full logic that boundary and your initial terminal condition define the financial problem, ensure uniqueness, translate contract terms into mathematics, produce stable and tradable prices. The clean table here is that please understand that if you're trying to answer the question, what is the payoff at maturity condition, that answer is the terminal condition. If you're trying to answer what happens if stock price is zero, that is the boundary condition. If you're trying to answer what happens if stock price is extremely high, that is again a boundary condition. If you're trying to explain what is the current market state, right, that's the initial condition. And if you're trying to get how do we get a unique price, that is partial differential equation with condition, right? You look at into quant finance, quant area is pricing. Why condition matters? Because gives correct derivative value, that is one. Risk management gives stable Greeks, portfolio optimization define objective value function, numerical methods prevents unstable finite different rates, model validation ensure economic intuition is respected, right? The key line to remember here is that PDE gives the rule, boundary and terminal conditions define the contract. Okay. Then we get into the question, guys. Question number 1 to 3. Now let's just shift to practical questions. First is identify initial and terminal conditions for a European call option and explain their role. See, this is easy, right? This is what we have done multiple times, right? To prepare, right? Terminal condition here is Vs comma T is equal to your max S minus K comma 0 is the payoff maturity. The runtime value is Vs naught, right? But usually Vs naught is what we solve for, right? Terminal is equal to Vs comma T max S minus K comma 0, which is the fixed payoff. The fixed is the payoff boundary at S is equal to 0, right? At S is equal to 0, V 0 comma T is equal to 0. At large S, V S comma T S minus K exponential minus R exponential S minus K T minus T, right? So fixes payoffs in the first condition. This is one call worthless if stock is 0 or less than strike, right? Call behaves like forward exposure, which we saw, right? Then write the Dirichlet boundary conditions for a European put option and explain intuition again for European put. All the solutions are already given, guys. I'm just trying to give you an understanding, right? Delayed solution is already given. BST is equal to max your K minus S comma 0, V of S comma T equals maximum K minus S and 0. Stock price effectively becomes very large, right? VST tends to 0 as S tends to infinity. If the stock price is extremely high, right? The right to sell at a fixed strike is kind of worthless. So V0 at S is equal to 0, right? At S is equal to 0. Your European put, right? Right, V0 comma T. K exponential minus R T minus T, right? Because the stock is 0, the put will pay K at maturity discounted back to today. Okay. Next one is explain the Neumann, right? Boundary conditions. I interpret this again. Partial derivative of V with respect to S tends to 1 as S tends to infinity. This means delta approaches 1 for a deep in the money call, often behaves like the underlying stocks. Deep out of the money call, delta near 0, at the money call around 0.5. Broadly speaking, deep in the money call near 1. This is useful in numerical pricing because the PDE grade needs sensible slope behavior at large S. Right? That is what we need to understand. All the solutions are given ahead, guys. I'm just trying to give you an idea. Okay. Question number 4 and 5. Explain numerical option inequality condition and free boundary concept. Again, basically, when you look at your numerical option, inequality condition, free boundary condition, right? See, these are important because they show that boundary condition are not only for simple European option, right? Similarly, for this one also, identify initial and boundary condition in specific amount pricing and explain the impact. So if your product model is your American option, right? Condition type is early exercise boundary. If your product model is bonds, condition type is maturity redemption condition. If your product model is interested model, condition type is rate boundary behavior. Your product model is callable bond, condition type is exercise call boundary. The product model is portfolio optimization, condition type is sustained boundary, right? So that is what we try to understand Okay, then again, we look at solution. The slide gives us terminal condition. This is what I was talking about. We can see that economic role is that fixes payoff at maturity, ensure unique PDE solution at the starting point for backward pricing. Right, that is what we have seen already. Payoff, we know that before maturity, the option has time value. The PD tells us how the time value evolves backward from maturity to today. The terminal payoff anchors the final value in the PD. Discounts and adjust the payoff backward under your risk neutral dynamics. Okay, then we get into the next solution. Again, this also we have seen S tends to infinity. We have VS T tends to 0. This is correct and intuitive. The put option gives the right to sell at strike K. If the stock price becomes extremely high, nobody wants to sell for K because the market price is much higher. So S is equal to 0. Put value intuition is very valuable. S equal to K. Add the money. S tends to infinity. You are worthless, right? So remember, this is put option, right? Okay, this boundary condition is used in finite difference grades to make sure the right hand side of grade behaves economically, right? So payoff becomes worthless at a very large S. Payoff fixed at maturity with Dirichlet condition. Then we get into the next part, solution number 3, which is Neumann condition, specific derivative rather than value, which is given. Financial meaning is option behaves like underlying asset at high S. Delta approach is 1, improves stability in numerical systems. Numerical schemes applies mainly to call option very high stock price. Why does delta become 1? For the deep in the money call, right? Let's say, V S comma T is equal approximately, right? S minus K exponential minus R T minus T, right? So, del V by del S is equal to almost equal to 1. So the option move almost 1 for 1 with the stock. Okay, stock moves by 1, deep in the money call approximately moves by 1. Stock moves by 10, deep in the money call approximately moves by 10. Stock moves by 100, deep in the money call approximately moves by 100. That is why delta tends to 1. In risk management, this matters because delta tells us how much stock exposure the option creates, right? Improves stability in numerical system, right? Okay. Then we have solution question 4. This slide gives you VST, kind of greater than equal to intrinsic value. V of S comma D is greater than equal to intrinsic value, right? So Vs comma D is your max, VPD comma intrinsic. Again, V of S comma D equals the maximum of V from the PD intrinsic value. This is a very important idea for American option. Unlike your European option, American option can be exercised early. For every point, investor compares to choice. Continue holding, keep the option alive. Exercise now, take intrinsic value immediately. Exercise. And therefore, V S comma T is equal to max of your continuation value. This we have seen earlier in the previous chapter also, right? And exercise value. Okay, so slide writes that as V S comma D to max VPD comma intrinsic. The free boundary is the unknown line that separates. If the region is continuation region, meaning do not exercise. If the region exercise region, exercise now. For an American put, there is usually some critical stock price S star T. If stock falls below that level, early exercise may become optimal, right? So S, right, this part means exercise may be kind of your optimal. This boundary is called free because it is not known in advance. It must be solving with the PD. I know simple close form here because the exercise boundary moves over time. That makes the problem more complex than European option. European option exercise only at maturity. American option exercise anytime. European option fixed terminal payoff only. American option is early exercise constraint. European option closed form Black-Scholes solution available. American option usually numerical method needed. European option simpler PD, American option PD plus inequality or free boundary. This connects directly to finite difference method, binomial trees, and Longstaff, Shor's, Monte Carlo, right? LSM. Okay, so please understand that, right? All these will come ahead at the right time, guys, but just understand. Question number 5, last but not the least, the slide gives you PDT is equal to 1, right? P of T comma T equals 1. This means at maturity, a 0 bond pays 1 unit of money. For example, if the bond face value is 1, then maturity, its value is 1. Important decision point is the slide calls this an initial condition, but it's standard by your bond pricing notation, right? It is generally written P, T, comma T, right? So anyway, like you find that also is fine, right? Use price at time t of a bond maturing at t. So PDT is equal to 1 is more accurately a terminal condition because it is a value at maturity. Right? Vasicek intuition here in the Vasicek model, the short rate follows your DRT A B minus RT dt plus sigma dWt. Right, RT is the short-term interest rate, A is the speed of mean reversion, V is the long mean rate, sigma is the interest rate volatility, dWt is the long motion shock. The bond price depends heavily on the interest rate level, interest rate movement, rate rise, bond price falls, rates fall, bond price rise. This is exactly what the slide says. R greater than R increases, price falls, R decreases, price rises. When rates goes up, price goes down. When rates go down, price goes up. This is the core fixed income concept, right? And look to the risk management. The concept is bond rate, high rate. Practical use is bond price should be low, bond rate, low rate, bond price should be high. PGD is equal to 1, bond redeems at face value, rate sensitivity, duration, and DP01, dollar value of 0.1 with movement, right? Numerical stability prevents unrealistic bond prices. So for Vasicek bond pricing conditions, make sure the model respects basic discounting logic, right? So final idea here is everything, if you want to join together, you look at terminal payoff for call, we understand the formula is V S comma T max S minus K comma 0, right? For terminal payoff for put, we have seen question number 2, V S comma T max K minus S comma 0, which is basically your put payoff at maturity. Dirichlet condition V X T X comma T is equal to G comma T, V of X comma T equals G comma T, which fixes value. Neumann condition is partial derivative of V with respect to X equals H of T, which fixes sensitivity. Then your call high price delta is delta tends to 1, call behaves like stock, leave in the money. American inequality V S comma T greater than equal to intrinsic, V is greater than or equal to intrinsic value, which is early exercise floor. Then bond maturity condition PTT is equal to 1, which is basically P of T comma T equals 1, bond pays par at maturity, right? So boundary and initial terminal conditions are what? Convert a general partial differential equation into a specific financial pricing problem. They encode the payoff, your market limits, your exercise rules, your economic behavior needed to produce a unique, stable, tradable price. Okay, so keep that in mind, guys. Okay. That's it, guys. Small chapter, not very long, lengthy, but go back and revise it, right? Very, very important because a lot of concepts will come ahead, right? Dirichlet condition, Neumann condition, boundary condition, terminal condition, initial condition, how it is used in trades, how it is used in American option, how it sets the floor, how it is used for sensitivities, how it is used for option pricing, call option, put option pricing, Greeks, right? So very, very important, right? Very, very important. Go and revise at least twice. You'll be totally fine. And I'll see you in the next lecture. Okay. That's it, guys. That's it for this one. I'll see you in the next lecture. And we'll continue our journey ahead. Okay. All right, guys. Thank you.